Good morning, everyone, and thanks for joining us today. I am Marcello Bruno, an application engineer here at Engisoft, and today I am the chairman during this webinar. The topic today is battery degradation. That is, let me say, something it's challenging everyone in this field. It is a complex physical process. Some phenomena appear, such as solid electrolyte interface, lower growth, lithium planting, and surface cracking. These phenomena make the prediction of battery degradation hard to have. In addition, we have a lot of unknown parameters. Here with us today, we have Vinit David. Vinit has a PhD in mechanical engineering from Purdue University and has over 2 decades of experience in the energy sector, simulation, and mathematical modeling. He also brings experience in product management and sales across global markets, including the USA, Europe, Southeast Asia, and India. 2 years ago, Vinit founded Urja with the goal of simplifying the design process for complex engineering problems, particularly in the battery field. Today, Vinit will be sharing his expertise and his approach to the lithium battery degradation with us. Hello, Vinit, can you hear me?
Yes, I can hear you loud and clear. Hello.
Hello, Vinit. First of all, thank you for being with us and for sharing your expertise and your studies and your idea. Before moving to the presentation, I would like to give our participant a little bit of information, just 3 points. First of all, for question, you should see the Q&A toolbox in the Zoom window where you can write your question. Vinit and I will answer them after the Vinit's presentation. Second point, we are recording this webinar and you will receive an email with the link to watch the video again, if you want, of course. That last point, in order to improve ourselves, we will send you a very short questionnaire with just a simple question. We really appreciate if you answer them. So Vinit, if you are ready, please share your screen.
Yes, thanks a lot, Marcelo. Thank you for the introduction. Appreciate it. And happy to be talking about battery degradation, especially for real world conditions to the audience here today. As Marcelo mentioned, feel free to type in your questions at any time during the webinar, and we'll make sure we get to all the questions after we're done with the presentation. Let me just dive into the presentation by giving you a very quick overview to Urja. We are a young deep tech company, and our mission is to simplify complex engineering all the way from design to deployment. We are doing that. We're starting with the field of battery modeling, all the way, like I said, from design to deployment, especially because in the field of predictive modeling of batteries, I think it is well established now that pure physics-based models and pure physics-based approaches are insufficient in capturing the predictive analysis problem of batteries. And therefore, we are using a hybrid approach where we use a combination of physics, of course, all the available physics that we have to us, as well as the minimal amount of data that we have available to us, especially at the beginning of any product design cycle. We merge both of these together. We merge the physics that we have with the data that we have and couple them to enable reliable and fast predictive analysis of batteries, all the way from the concept design stage to a stage where batteries are deployed on the road as well. And I'll come to this a little bit in more detail as we go on. But like I said, predictive analysis of batteries is an especially challenging problem today, as I'm sure we all know. Everybody who's gathered here knows. And today, I think the current approach is you do a combination of accelerated testing, and then you build some physics-based models. And I would say physics in quotes here, and I'll explain why I'm saying that in a couple of slides, in order to predict how your batteries are going to behave in a real life situation. Now, the challenge here is, of course, that accelerated testing is, of course, it's the only option we have, considering we can't run these tests for several years, which is what it's necessary to capture aging in batteries, especially aging in batteries. And therefore, we have to somehow figure out how to combine the data, or extract information from the data we get from accelerated testing, fit it into pure physics based models, and then do some predictive analysis. And the biggest challenge with doing that is that while all of these models work excellently in the estimation zone, which is the zone for which you have data available, because of the sheer number of parameters that are required to set up the physics-based models, it is often seen that in the prediction zone, the results don't really match what you would see in real life conditions. And this is for a variety of reasons, of course, because first of all, you are trying to extract information from accelerated life testing and then use it for predictions on real life, which causes some changes in the parameters. Secondly, it is very difficult with current techniques to optimize for all of the parameters that you need in order to perform these kinds of accurate analyses using physics-based models. And also because it's a highly non-linear problem. The electrochemical problem of batteries is highly nonlinear. It is extremely sensitive to, as an example, temperature, C rates, the depth of discharge, the SOC, I think predominantly amongst the many other variables that it is, and the many other derived variables that it is sensitive to. And all of this can lead to poor predictions as you keep on moving forward in time. And that is the reason the hybrid approach works, because physics-based modeling is deterministic to begin with. And more importantly, while we may believe that we understand the physics of the battery, the reality is that we don't. Even Marcelo, to begin with, talked about some degradation mechanisms like SEI layer growth as an example. And while we may claim, we as a community may claim that we understand the physics of SEI layer growth, at the end of the day, it is still an empirical model. Therefore, we need parameters in order to fit the SEI layer growth to our particular form factor and chemistry. And therefore, what I'm trying to emphasize here is that we don't have a complete handle on the physics. We have some amount of physics. Using partially complete physics and then expecting accurate, predictable, reliable results is obviously not going to work, which is why data is important, because with some amount of data, you inherently account for the uncertainty in the model. So you combine the physics can be used in different ways. You can use it as synthetic data to generate synthetic data. You can also use physics in machine learning. So we use all of these different approaches to ensure that at the end of the day, the solutions that you get are both reliable as well as fast. And that's our goal at Urja. Therefore, I'll just dive into the fundamentals of aging, because this webinar is predominantly to focus on degradation modeling of lithium-ion batteries, specifically speaking. Of course, we have a diverse audience, I've been told, and therefore I'm going to start with a few fundamentals. So pardon me if I'm covering something which is already known to you, but I'll be brief with this. And if you have any questions and you would like me to discuss any of these things in detail, I would be happy to do that at a later stage. But really, aging is the loss of performance of the cell and the pack over time. And really, aging starts as soon as the cell is assembled. And of course, I don't want to get into the details here, but that is the harsh reality. It starts as soon as you assemble the cell, then you store it and you transport it and start using it. and it is triggered by certain physical processes which happen within the cells. So there's no way you can arrest aging, but it is accelerated by both operating conditions and environmental conditions. I say operating conditions as in the um, how it is stored, how it is used, as well as what temperature it is stored at, as an example. So let's look at what causes aging. As I said, it's a multitude of factors. Temperature, of course, is one of the biggest reasons that you can accelerate aging. But before we get to that, some common terms that are used in when we talk about aging. So there's SOC, which is the state of charge. Then you have the BOL, which is the beginning of life, the end of life, which is EOL. And then, of course, RUL is the remaining useful life. And then you have the depth of discharge and the state of health, all of which are terms we'll be using over the course of the presentation today. And so, like I was saying, the reason for degradation is a multitude of factors: the state of charge, the temperature. There are two types of aging. There's calendar aging and cyclic aging. Calendar aging is when your batteries are not being used, and cyclic aging, of course, when your batteries are being used. With calendar aging, you see accelerated aging, or aging increases at higher SOCs and higher temperatures. Similarly, with cyclic aging, depending on the pattern of usage, you can have increased degradation both at higher temperatures as well as at low temperatures, especially if you are doing fast charging at low temperatures, as an example. And the state of charge and the depth of discharge can also have a significant impact on the aging behavior. And of course, it is not just these individual stress factors, but a combination of these stress factors can also have a significant impact on aging. And the magnitude of the impact of this can be seen in this example. It's published data where you can see that if you have a suboptimally designed vehicle, it can lead to early degradation of the entire pack, which can lead to a lot of business impact on the OEMs. Now, the reason it is so challenging to capture or reliably capture degradation across battery packs is, like I said, it's a highly complex physical process. Not only is it highly complex, but there are a lot of several unknown parameters involved. Just to give you an example, and I talked about this earlier as well, some of the key factors which influence and accelerate degradation in batteries are something called the SEI layer growth, and not just really the growth of the SEI layer, but the as the battery keeps getting cycled and there's intercalation and reintercalation of lithium ions in the anode, and of course the cathode, but predominantly the anode. The reformulation and subsequent growth of the SEI layer is a challenging mechanism which impacts degradation. Then you have lithium plating, which becomes critical both when you're fast charging as well as when you're operating your batteries at low temperature. Lithium plating can also be a big safety hazard, because it can eventually lead to dendrite growth, which can lead to a short circuit in the cell. And then, of course, you have a continuous loss of the active material within the cell, and also particle cracking in the electrodes. All of these are the physical mechanisms which impact degradation in batteries. And as you can see, this is just an example of the equations that you have to capture. This is just a small example that I'm showing. Actually, in reality, I'm sure, as we all know, there are several other equations, many equations, and you can see each of the equations has several parameters which need to be fit. And that really is the challenging part of this problem, because you can see there are several mechanisms. Each of these mechanisms are related to other mechanisms, to the concentration, the temperature, and therefore the challenge is to capture this nonlinear system while ensuring you have the right set of parameters, which is a big nightmare. That becomes a big challenge, because now there are all of these different causes, uh, the SEI layer growth, lithium plating, particle cracking, loss of active material. All of these impact degradation in different ways. Not just degradation, but as I said earlier, this is also a safety hazard. We all know that thermal runaway is a big risk, and it has been well established that degradation can also impact thermal runaway, especially when you have lithium plating. It has been established that lithium plating will reduce T1. T1 is the onset of self-heating, as well as T2, which is the onset of thermal runaway. So both of these can be significantly reduced if you have lithium plating. So degradation will have a can increase the risk of thermal runaway, and that is also something which needs to be predicted. But the challenge is that all of this is difficult to do, because there are so many different physical phenomena involved, and they're highly sensitive not only to operating conditions, but also to how you drive the vehicle, how you store the vehicle, how you perform fast charging, and at what temperatures the temperatures that the battery is being exposed to. All of these variables, like I said, are very difficult to capture using only accelerated testing, which is which is a big constraint today. And really, and this is an analogy I came across some time back, and it's an excellent analogy. It's like an egg. You can't expect to boil the egg for 20 minutes at 100 degrees centigrade and expect it to hatch a chicken. You're going to get a boiled egg, and that is essentially what we do with accelerated testing. We stress the battery at high C rates, both for charge and discharge, but we cannot expect the predictions to give us real life behavior, which is a completely different set of conditions. And that really is what we are trying to solve with the hybrid approach that we have at Urja, where we take limited amount of cycler data, both for cyclic as well as calendar aging. We extract information out of this cycler data, and then we use this cycler data, or the information that we've extracted out of this cycler data, to predict how the battery is going to behave in real life. And so this is what we are trying to solve at Urja. And this hybrid approach is embedded into the application suite that we've developed, which I'll show you shortly. But our goal is to simplify the whole experience for engineers, because today we understand, that time is critical. You need to solve problems fast. These are big problems. You want to solve them while minimizing resources. So we have created an easy to use interface, a cloud-based interface, where you can log on, quickly set up your problems, solve the problems, and move on with your with your battery design workflow. So at this stage, I will share with you our Urja interface and show you how you can set up your problems in the Urja interface. So Marcelo, can you see my web browser?
Yes, Vinit, I can see it.
Excellent. So you can log on to our web interface. You can log on here at app.urja.energy, and you can sign in to our user interface. And this is how our user interface looks. For some reason, I'm not able to see the interface, but that's okay. Right. Can you still see the interface? The web interface?
Yeah,
No,
yeah,
we can't see it.
Yeah.
We can see the slides though.
Awesome. Can you see the interface now?
The presentation, we are seeing the presentation.
Okay, can you see the
Yeah,
interface?
now we see the interface, yes.
Excellent. So, all right, so this is how the interface looks. You can start creating your new projects within Urja here. You can also share your projects with your colleagues within your organization, and the goal really is to simplify the whole model creation and analysis process for the entire organization. And you can see this is how the whole application suite is set up. So you start by defining properties for your cell as well as for your pack, which I'll get to later. But just to give you an example, this is how you can enter material properties, cell properties. So you can enter the cathode properties, the anode properties, and the form factor. So we've tried to keep it simple for users who may not have uh, advanced exposure to electrochemical modeling. But for those of you who are experts in electrochemistry and who would like to enter their own material parameters and design parameters and the degradation parameters, we have the option for you to change all of the parameters that you may have access to. Of course, once you enter these parameters, then you also upload some data. And here, you can upload both different kinds of data. So you can upload HPPC data, cyclic aging data, as well as some other data, which we'll talk about later because it may not be relevant today. But once again, the goal is to simplify the whole experience for you. So as you can see, all you need to do is upload the data here. And with a single click of a button, we process the data for you, clean up all the chinks. You can modify the settings here if you want, of course, and make it ready for machine learning. So you can see we make sure that we clean up the data and make it ready for machine learning. And once you have uploaded your data, the HPPC data, the cyclic aging data, and we've extracted the information from it, you can then go to the to the fade physics that we have, or the applications where you can start working with the data and start performing these predictions. So it's a two-step approach. You first train the models and then you perform the predictions. So I'll quickly open some examples and show you what you can do. So you can link whatever model you are building, the training model, to the data that you have uploaded into the interface. You can choose the number of training cycles that you want. You also have, again, the advanced users amongst you. While we do the parameter optimization for the different degradation parameters, have the option to set up the lower bounds, the upper bounds, the initial guess for all of the different degradation parameters. You can also choose which parameters you want to optimize for. So you can do all of these things, and we perform an optimization based on that. And once we've performed the optimization, you can then start performing your predictions. So in the predictions, you link it to a training data. You choose the number of prediction cycles that you want to go to. You have different options. You can choose SOC limits or voltage limits, depth of discharge as an example. You can choose to do predictions for a constant charge discharge, or you can also upload a drive cycle or a duty cycle of your choice. You can upload a temperature as well. You can have a time varying temperature. You can have constant temperature, ambient temperature, for instance. And you can also choose to switch on or off different degradation mechanisms if you want to explore the impact of different degradation mechanisms. And then you can solve these models where you can see what your state of health would be, the throughput would be, and you can also see the impact of different degradation mechanisms. So you can see what the SEI layer growth is, the amount of plated lithium, and of course you can export data to perform advanced analysis on different variables if you would like to do that. So this is the physics-based approach we have, where we do parameter optimization, and you can then do a full-blown physics analysis. We also have an interface for the hybrid approach, where you can, in a similar way, perform training. This is a pure machine learning model, so you can choose the data that you want training done on. And once again, it's an easy to use user interface. You can just choose the different data that you've uploaded. You can choose the different features on which you want to perform the machine learning. You have a choice of over 20 features from which you can select how you want to perform the machine learning. Then you perform the training here. And once you've performed the training, then in a similar fashion, you have an interface where you can choose the training data and perform the predictions. Now, again, if you have any questions on what kind of models we have, all of the details are given in the documentation up here. So you can see the documentation here. You can see what we are solving for, how we are solving for it. All of the details are given, both the physics part as well as the machine learning part. So you can see the details within the interface itself if you have, if you need any confirmation on what kind of models we are using. So this is how our user interface for capacity fade looks, where you can model degradation. I'm just going back to my presentation. So these are the kinds of analysis that you can do, and we've done a lot of validation of our of whatever we've built with other softwares, and you can see that we are close to 10 times faster than existing physics-based software, as well as more accurate. And again, the accuracy comes from the fact that we can inherently account for the uncertainties that come about because of both the operating conditions as well as manufacturing defects. So these are some of the validation cases that we've run. Here's an example where we've done training on 200 cycles, the first 200 cycles of an experimental data set. And then we performed the validation or the predictions for the subsequent 750 cycles. You can see that there's a very good prediction. Not only are we able to predict the state of health, but we are also, for a given cycle, you can also predict the voltage response at a given cycle. So that is also something that you can extract from the predictions that we perform, due to which you can perform power fade, for instance, if you want to, during the once you've set up your problems. So as I said, using this combination of physics-based modeling and the hybrid approach that we have, you can perform degradation analysis and predict the SOH, the end of life, for different criteria. Here's an example where we have considered different temperature cycles for different Indian cities and demonstrated the impact of different climates on the state of health or the life of the battery pack of this vehicle. And actually this was done on a vehicle which is actually running on the roads of Delhi in India, and we've validated this with existing results. You can also see how the range changes. In this case, it was an air-cooled battery, so you can see the significant impact that the ambient temperature had on the range, which is something we predicted. And then when we introduced cooling, you can see how the range increased over a period of 3 years. So these are the kinds of analyses that you can do. As I said, you can upload your own customized drive cycles as well as duty cycles and predict how the vehicle is going to behave over a period of time. you can predict the range of the vehicle, you can see the impact of fast charging, and here in this case you can see that in this case where we did constant charge discharge cycling, this is a pure prediction. You can see the impact of high C rate charging and discharging on the life of the vehicle. This is an example where while we predict the SOH, we have also predicted the voltage response for a given cycle. So on the left hand side, you see the voltage response at the beginning of life and after 1,000 cycles. So you can see what impact degradation is going to have on your voltage cycles. You can also see what impact, as you can see in this curve, the depth of discharge is going to have on your voltage cycle. So these are the different kinds of analyses that you can run. Just as you can see the impact of the depth of discharge and the temperature, you can also get insights into the dominant degradation mechanisms, whether it is SCI layer growth or loss of active material. All of these kinds of information can also be extracted from the analyses that you do with us. And as I said, we've done a lot of validation, and for this particular cell, an LG M50 cell, a 1,000 cycle analysis, which took 24 minutes in a open source tool and 6 hours in a popular physics based tool, we were able to do in less than 2 minutes. The advantage of having achieved this speed at the cell level is that we can now also do these kinds of analyses at a pack level. So you can actually predict the degradation at a pack level. You can account for the relative initial variation of SOH, the impact of temperature, varying temperature across the pack, and you can account how this is going to lead to cell variation in the SOH as the pack gets used over time. So that is what we offer. As as we start using batteries more and more in our daily applications, there are several challenges that we face, all the way from cell design to cell qualification to integration of the cells into a pack, packaging, designing the battery pack, and then analyzing pack safety, on to designing the BMS, where you have to decide on the BMS limits, decide where to place the sensors, how to program to optimize the user experience, come up with fast charging algorithms. At Urja, we have created products which align with all of these design needs when it comes to battery pack design. So these are the different apps that we have. I focus today only on degradation, but we also have apps for the pack thermal behavior. So we have apps where you can design your complete battery pack, design the different material, optimize the different materials that are needed, the cell spacing, to ensure that you design the pack to mitigate the risk of thermal runaway, as an example. We also have apps where you can a priori predict the range of your vehicles for different scenarios, predict how the range is going to behave as there is a degradation, thereby ensuring you create your BMS algorithms in a manner which optimizes the user experience. So all of these are also features which are available in our interface. And at this stage, I would like to conclude the presentation and start having a discussion with all of you. And of course, I'd love if you have any questions. I think Marcelo can also help you. And if you'd like to try out our software, feel free to reach out, and you can just log on to our interface. No need to install anything, and start using the software. Thank you.
Thank you, Vinit. Very interesting. I read a lot of questions. We can, if you want, we can answer them.
Sure.
I'll share my screen. Okay. First question is, could you show us how the real world data should look like to train the model?
Absolutely. So good question. It's thanks for asking that question. To begin with, I want to clarify that the interface that I showed you today is an interface that that you use for design optimization of both both the cell and the pack level at the beginning of the design life cycle when you don't have real life data, and therefore all the interfaces that I showed you support only cycler data. So you can upload cycler data. Having said that, we are also working with real life data, and we are using that in combination with physics-based models to predict how batteries will behave later on in their life once they're deployed in the real world. But we don't have an interface for that because this is a very challenging problem, and it really, so we are working closely with OEMs who want to predict battery behavior once the vehicles are deployed on the road. So this is a customized solution that we offer using real life data for training. And if you're interested in that, I'd urge you to talk to Marcelo, and we can show you how it is done. But the user interface that I showed you only supports uploading of cycler data. Uploading real life data is something which we can do, but that's something we'll discuss with you if you reach out to us. Yeah, so that's sort of the answer to the question.
Thank you, Meet. The second question is, what is the minimum number of cycles you have to give the model to give accurate results? And what is the advised number of cycles to get a very good prediction?
Yeah, thanks. Again, I think a very interesting and pertinent question. And so, not just the number of cycles, for sure, the number of cycles is important, but also ensuring that you're at least covering the range of the critical operating conditions that you would like to use your predictions for. To answer your question specifically, the minimum number of cycles would be 200, I would say. But I would advise anywhere between 250 to 300 cycles. 300 cycles is very good for sure, but 200 cycles is also decent. Apart from that, I would also request that you upload data where you capture the range of temperatures. So for HPPC data, it would be good to have 45 degrees, 25 degrees, and 5 degrees. For cyclic aging, 25 degrees for sure, low temperature data and a high temperature data. Similarly, for C rates, at least one low C rate, 0.5 charge discharge, and one C charge and discharge would help us capture the entire range of C rates, temperatures, and charge discharge cycles.
Thank you, Vinit. Another question, we have a lot of questions. Another question is, I just saw that you can select NMC as cathode material. Can we also select NMC 811 or NMC C22?
Absolutely, good question. Right now the defaults we have are only for NMC, but as I said, there are two things that you can do. If you are using, a particular chemistry within whatever you're using, you can, and you have access to the parameters, you can upload those parameters as I showed you. If you don't have access to those parameters, like I said, if you upload the cycler data, then the information that you when you choose NMC as a default, the parameters that we select without giving too many details are an initial guess, and then we use the cycler data for your particular chemistry, whether it's 811 or 622 or whatever it is, to actually come up with the appropriate transport design material parameters, as well as, of course, the degradation parameters. So we get the right information from the cycler data. So that's the answer to the question. Right now, either enter your own parameters or rely on using data to get the right set of parameters.
Thank you, Vinit. Another question, we are working on the fast charging algorithms for our batteries. How Urja can help us?
Yeah, great question again, and for sure we can help you. So, like I said, we have all of the physics-based models, the SPM and the DFN. And when it comes to fast charging, basically you want to make sure that you don't breach the the lithium plating line, right? So you make sure that your voltage is below the lithium plating line, because if you breach that voltage, the over potential for lithium plating, then you start having lithium plating while fast charging. So we have come up with algorithms where you can automatically detect the lithium plating line, and then we tell you the current to maintain so that you are at the lithium plating line when you're doing fast charging. So that's how you can we can help you come up with a fast charging algorithm.
Thank you, Vinit. The last question, in what manner do you account for the effect of terrain on degradation, such as hilly terrain versus flat terrain?
Yes, great question again. So again, I didn't show this to you, but we have different apps. We have an app called the Range app, where you can upload your velocity versus time drive cycle, which is something you would conventionally find in available data. And you can specify your vehicle specifications, the weight of the vehicle, whatever other constraints you have on the vehicle, as well as the terrain. You can account for a gradient, you can account for different gradients. You can also upload your own terrain information, and we extract the current versus time drive cycle for this set of operating conditions and the velocity versus time drive cycle. So this is how you can account for your terrain information in our software.
Thank you. Another question. Do the 300 recommended cycles also apply to LFP chemistry or any other chemistry which can provide more than 2004 cycles?
Okay. Absolutely, in our experience, I mean, like I said, we've performed a lot of validation. I think the validation I showed you was for an NMC cell, but we've performed validation on LFP as well. And we have seen this, the 300 cycles that I talked about has been able to take us up to 2,500 cycles. We'd be happy to share all of our validation data with you, where you can see the validation for NMC, NCA, and LFP.
Thank you, Vinit. So I think we don't have any other questions. So thank you once again for joining us. And thank you very much, Vinit. And we hope you have found this webinar interesting. And if you want any other information, don't hesitate to contact me. And please don't miss out our next webinar about batteries, and in particular about thermal runaway. You will find more information on our website in the coming day. So we need once again thank you for your presentation, and have a nice day. Bye.
Thanks a lot. It was good talking to you. Bye.
Bye, everyone.